What we have been doing up until this point is to take the Laplace transform of a simple function. So the Laplace transform of a function, let's say Laplace transform of f of t or f of tau, right? So in this video, we are going to do something special. We are going to take the Laplace transform of an integral. So what if we are asked to take the Laplace transform of the integral from 0 to t of f of tau d tau? So how do you find the Laplace transform of this? And this one has a very interesting answer. So I'm going to prove this result in two different ways. So the first method, I'm going to use integration by parts. So the first method, so I'm going to prove this one in two different ways, and the first method is integration by parts, in short IBP. So this is what I'm going to use. So let me go ahead and refresh your memory with the definition of the Laplace transform of a function. Let's say f of t, why not? That's what we have been using. So this is the integral from 0 to infinity of e to the negative st. This is multiplied by the function that we are seeking to transform, and then dt. Right, so using the same definition, we can define the Laplace transform of this integral. So the Laplace transform of this integral, that is the integral from 0 to t of f of tau and then d tau. This one is equal to, so we are going to have the integral from 0 to infinity. This is constant. E to the negative st is constant as well, and then we are going to multiply it by what we are seeking to transform, which is the integral from 0 to t of f of tau d tau, right? But don't forget to add the dt at the end. So this is what we have, right? So here I'm going to use integration by parts, IBP, as I already told you. Normally we will have to differentiate something and integrate something, right? So looking at this integral, what are we going to differentiate? I am going to differentiate this, that is the integral from 0 to t of f of tau d tau. This is what I'm going to differentiate, and I'm going to integrate the rest, that is e to the negative st, right? So all of this we are differentiating with respect to the time. So this is what we have. So this one is plus, next one is going to be negative. Alright, so let's do the easy one first. So integrating e to the negative st, that is going to be negative 1 over s e to the negative st. That is integrating with respect to time. How do you differentiate this integral? So I'm going to refresh your memory with what we call the fundamental theorem of calculus. So this is what we call the fundamental, right, theorem of calculus, fundamental theorem of calculus, part 1. So this one is part 1, fundamental theorem of calculus, part 1. So this one, it says that, so let me make it more colorful. So this one, it says that if we are differentiating with respect to time ddt of a certain integral from 0 to time of f of x dx, this one is just equal to f of t. Right, so this is from the fundamental theorem of calculus. We can box that. This is very important in solving this Laplace transform. So now, using that same principle, how do you take the derivative of this integral? So from the fundamental theorem of calculus part 1, this one is just equal to f of t, right? So because this one, differentiating this one with respect to time, is the same as this. Alright, so now this is what we have. So normally what we do, we will have to multiply diagonal terms. When we do that, there is no integral. We are done with the integration. But when we multiply terms horizontally, we have to take the integral, right? So the Laplace transform of the integral, which is the integral from 0 to t of f of tau d tau, right? This one is equal to what? So now we are going to use the integration by parts, multiplying diagonal terms. That is going to be negative the integral from 0 to t, right, of f of tau d tau, right? But we will have to multiply by 1 over s times e to the negative st, right? This, so we are done. Then we can put the limits of integration from 0 to infinity, right? And now negative negative, when we multiply terms horizontally, we will have to what, take the integral. So we have the plus the integral from 0 to infinity of multiplying them horizontally. So that is going to be 1 over s e to the negative st, and this is multiplied by f of t and then dt. All right, so this is what we have. So we can see that the problem now is how to take the limits, right? So the limits of integration, f of tau d tau here. So this one is equal to, so now let's take the limits of integration. So we are done with integration here. So we are going to take the limit as t goes to infinity. That's the upper limit of the integral from 0 to t of f of tau d tau. Right, and this is multiplied by 1 over s e to the negative st. This is the upper limit minus the lower limit. We are going to take the limit as t goes to 0 of the integral from 0 to t of f of tau d tau, and this is multiplied by 1 over s e to the negative st. So this is the limit, and then we are going to add this integral. So that is going to be 1 over s outside because it has nothing to do with t. The integral from 0 to infinity of e to the negative st multiplied by the function f of t and then dt. Cool stuff. So now the Laplace transform of the integral from 0 to t of f of tau d tau, this one is equal to negative. Now let's plug in the limit. So if we take the limit as t goes to infinity, so this one is going to be approaching negative infinity because s is a positive number. So after that is going to negative infinity, everything here is going to be 0, and then 0 multiplied by this one is going to be 0, right? So this one, if we are evaluating the limit, is going to be the integral from 0 to infinity because t is infinity, and then we are going to have f of tau and then d tau, and then the limit as t goes to infinity of this one is going to be 0. So this one is going to be 0. Now minus the limit as t goes to 0 of this. So this one is going to evaluate to 0 as well. The reason is if we take the integral from 0, t is also 0. So that is the integral from 0 to 0 of f of tau d tau. And this is multiplied by 1 over s because as t is 0, this one is going to be 1. Alright, so this is what we have, and then plus 1 over s. This one is the Laplace transform of the function f of t. That is the definition of the Laplace transform of the function. Alright, so the limits will evaluate to 0, then we are going to have the integral from 0 to t, the Laplace transform of that of f of tau d tau. Right, this one is going to be equal to 1 over s times f of s. Alright, so you can just write it like this, f of s over s, like this. So this one is left with f of s over s. Right, so because this one is going to be 0, 0 multiplied by this one is 0 regardless of what this integral is. And this integral, the integral from 0 to 0 is 0. The limits do not change. So how to take the Laplace transform of an integral? You just have to find the Laplace transform of the function that you are integrating, and then we just divide by s, and that will be the Laplace transform of the integral from 0 to t of the function. So this is the first method. So now let me switch colors and then we'll look at the second method. Right, so this one is the second method. So the second method, this is what we have. So now let me write the definition again. So the Laplace transform of the integral. So the integral from 0 to t of f of tau and then d tau. This one is equal to, right, the integral from 0 to infinity of e to the negative st. This is multiplied by the integral from 0 to t of f of tau d tau, and then we are going to multiply by dt. So we are going to multiply this one by dt outside. So now let me write this one in form of a double integral. So the integral from 0 to infinity, the first one. The second one is the integral from 0 to t of e to the negative st. This is multiplied by the function f of tau d tau and then dt as well. And this one is a Laplace transform of the integral from 0 to t of f of tau d tau. Alright, so what can we do here? This one, that means we are integrating first with respect to tau. That is this one. I'm sorry about this. We are integrating first with respect to tau, which is what we have here, and then later on with respect to t. but we can't easily integrate with respect to tau because we don't know the functional form. This function f of tau, we do not know what it is. So the ideal thing to do here is to switch the limits and then integrate first with respect to t, because it is very easy to integrate this one with respect to t because this one has no t. So we can easily integrate the exponential function with respect to t and then later on with respect to tau. So if I can switch the limits, then I'm in business, right? So we will have to switch the limits, but these limits, we are not integrating this one over a rectangular area, so we can't easily integrate the limits, we can't easily switch the limits of integration because we don't have a rectangular region. So this one is what we call the Fubini's theorem, right? Fubini's theorem. So if we have a rectangular region, then we can easily switch the limits of integration, but as it stands now, I can't switch the limits. So let me draw the area of this region, and then we will see what that is. So we have this. So permit me to call this one the tau axis. That is the horizontal axis is the tau axis, and the vertical axis is the t axis. So this is what I have, and then I am going to draw this. So that means that t is running from 0 to infinity. So t is equal to 0, and at the same time t is equal to infinity, and then tau is equal to 0, and at the same time tau is equal to t. So we are integrating with respect to t and then tau, but then tau is dependent on t. That's why you don't have the rectangular region. So let me plot this and we see what that region would be. So first, let's start with t. So when t is equal to 0, it means we are just moving on the tau axis like this. And then we have t to be equal to infinity. Infinity is a very big number, so but let me say infinity is somewhere here. That is t is equal to infinity like this. So I'm going to draw it like this. Why not? So this one is infinity. So the second one, tau, when tau is 0, it means we are moving along the t-axis like this. This is when tau is equal to 0. So this one is when tau is equal to 0. This one is when t is equal to 0. And then this one is when t is equal to infinity, right? And the next one is when tau is equal to t. When tau is equal to t and we have t and tau axis, it means the line is just passing through the origin like this. So this line is when we have t is equal to tau, or tau is equal to t. It's the same thing. So we see that this region here is a rectangular region, right? So that is a triangular region, not a rectangular region. So it means if we want to switch the limits of integration, we will have to redefine the region. So this is what I have. So now let me first start by integrating first with respect to the t, right? So I want to switch the limits and integrate first with respect to t and then later on with respect to tau. So let me do that by redefining the limits of integration for t. So t is the vertical axis. So if I'm moving from here to here, what will be the starting point and what will be the end point? So I'm going to write the limits of integration for t like this. So t is starting from what? So t here is equal to tau, why not? So t is starting from tau and it's moving all the way to what? Infinity. So it's moving all the way to infinity. So those are the redefined limits of integration for t. What about tau? Tau is the horizontal axis. It means we are starting at this point and then we'll move until we meet this line here, right? So like this. So where is tau starting from? That's the integral. From tau is starting from what? Tau is starting from 0 here. So it's starting from 0 to what exactly? Tau is starting from 0 to, let's say, t, but t is moving all the way from 0 to infinity. That is moving all the way from 0 to infinity here. So tau is going to move from 0 to infinity as well, right? So this is how I can redefine the limits. So we are now switching the limits of integration between the t-axis and the tau axis. So this one is now going to be e to the negative st and then f of tau, and then next first one is going to be the t, and the last one is going to be the tau. These are now the limits of integration for t, and these are the limits of integration for tau. Alright, cool. So this is what we have, and then we are going to have this, the integral from 0 to infinity of f of tau, right? Because this one has nothing to do with t, and then we have the integral from tau to infinity of e to the negative st, and then dt, and all this one is multiplied by the tau outside, like this. So this is what we call the Fubini's theorem. That is, if you have a rectangular region upon which you are integrating, we can easily switch the limits of integration. So this one is the Laplace transform of integral from 0 to t of f of tau d tau, like this. So the Laplace transform of the integral from 0 to t of f of tau d tau. So now let's integrate this, right? So we can easily integrate this. This one is going to be the integral from 0 to infinity of f of tau, and then this one, integrating this one, is going to be negative 1 over s e to the negative st, the limits of integration from tau to infinity, and all this one is multiplied by d tau. Alright, so now let's take the limits of integration. So let me write this one all along. So the integral from 0 to t of f of tau d tau, the Laplace transform of the integral from 0 to t of f of tau d tau, and this one is equal to the integral from 0 to infinity of f of tau. Now if we can take the limits of integration, so we have the limit as t goes to infinity of this negative 1 over s e to the negative st, and then minus, if you plug in tau, that is going to be negative 1 over s e to the negative s times tau, which is s tau, like this, and this one is multiplied by d tau. I'm just plugging in the limits of integration, nothing special. So this is the integral from 0 to infinity of f of tau, right? So now as t is approaching infinity, this one is going to be approaching negative infinity, and everything here is going to be approaching 0. So now you have 0 minus 1 over s, and that is going to be positive 1 over s e to the negative s times tau, and then d tau. So 1 over s is a constant in the tau world, so I'm going to pull it out. Then I'm going to have the integral from 0 to infinity of e to the negative s tau, and then multiply by f of tau, and then d tau. And this one is the Laplace transform of the function, the integral from 0 to t of f of tau d tau, like this. So that means that the Laplace transform of the function of the integral from 0 to t of f of tau d tau, this is equal to 1 over s, now multiplied by this one is the Laplace transform of the function f of tau, Laplace transform of the function f of tau, like this, and this one is equal to capital F of s all over s. And we see that this one matches with the answer from the first method. So capital F of s over s, and this is what we got from the first method. So the first one is integration by parts, and the second one is just by switching the limits of integration and modifying the limit. That's what we call the Fubini's theorem. So we modify the limits because we want to have a rectangular region over which we are integrating. So this result is cool, right? So it means whenever you are asked to take the Laplace transform of an integral from 0 to t of a certain function, we just have to take the Laplace transform of the function and then we divide by s, and that should be the answer. So let me do a very quick one for you to see. So a very quick example and see how this is applied. So let's say you are asked to take the Laplace transform of the integral from 0 to t of, let's say, sine of t, and then dt. I'm sorry, this should be sine of tau and then d tau. So let's say you are asked to take the Laplace transform of something like this. So with this one, you don't need to do something special, you just use the formula. So the formula is f of s over s. F of s here is the Laplace transform of this function sine of tau. So you just have to take the Laplace transform of the sine of tau and then you divide by s, and that should be it. So this one is equal to the Laplace transform of the sine of tau, like this, all over s. So that's it. So the Laplace transform of the sine of tau. So Laplace transform of the sine of tau is going to be 1 all over s squared plus 1 all over s. And this one is equal to 1 all over s squared plus 1 multiplied by 1 over s. And this is equal to 1 over s into s squared plus 1. That's it. So that means that the Laplace transform of the integral from 0 to t of sine of tau d tau, right, this one is equal to 1 over s into s squared plus 1, like this. So to verify this, why not differentiate this? So let's do this. So let's say we don't know the formula. We don't know the formula for the Laplace transform of the integral from 0 to t of a function to be equal to this, right? So to do this manually, we will have to do this. So the Laplace transform of this integral. So that means that we have to take the Laplace transform of the integral from 0 to t of the sine of tau d tau. This is now doing it manually. So doing this manual, this is what we have. So now we just have to integrate from 0 to t of sine of tau d tau. Right, so integrating sine of tau is negative cosine of tau. Then we plug the limits of integration from 0 to t. And this one is equal to negative outside. Plug in the upper limit, we have cosine of t, minus the lower limit, we have cosine of 0. So this is what you have. So the integral from 0 to t of sine of tau, right, d tau, this is equal to, this is going to be negative into cosine of t minus cosine of 0 is 1. And this one can be reversed with 1 minus cosine of t. So instead of using the formula, we can integrate first, and this is what we get. And now we are now going to take the Laplace transform of, instead of the integral from 0 to t of sine of tau d tau, we are now going to take the Laplace transform of that because they are the same. So 1 minus the cosine of t, like this. And this one, using the linearity property of the Laplace transform, this is the Laplace of 1 minus the Laplace of cosine of t, like this. So from our tables, Laplace of 1 is 1 over s minus Laplace of cosine of t is going to be s all over s squared plus 1 squared, which is 1. Now we can simplify this one to match with what we have. So the LCM here is s into s squared plus 1. This divided by this is going to be s squared, plus 1. Minus this one divided by this is s, and s times s on top is s squared. So in the end, we are getting 1 all over s into s squared plus 1, like this. And this one is equal to the Laplace transform of 1 minus cosine of t, which is the same as the integral from 0 to t of sine of t. Sine of tau, I beg your pardon. So this is what we have. And you see that this answer here is exactly equal to the answer we got from using our formula. So this is a very cool result. So you don't have to stress yourself taking the integral before taking the Laplace transform. You just have to know that the Laplace transform of the integral from 0 to t of sine of tau d tau is going to be the Laplace transform of the sine of tau over s. So whenever you are given a function to take the Laplace transform of the integral from 0 to t of a certain function, you just take the Laplace transform of that function and then you multiply by 1 over s, and that should be the Laplace transform of the integral from 0 to t of that function. So this is a very cool result that I wanted to show you. If you really find this video helpful, you give me a thumbs up and then subscribe to Calculus Diaries for more fun tutorials on Laplace transforms. So in my next video, I'll continue calculating the Laplace transforms of special functions. I would ask you to subscribe to my channel, like the video, and then I will see you in my next video.